All right. I hope my volume is okay. Let's see. We are recording not through Zoom, but through something else. It's 12:50, and this is, what is it, Wednesday, April 16th, and we are in section 5.7, the last section of chapter 5, the stuff that we're going to cover for the exam. All right. So in this chapter, we're going to talk about changing the variable in your multiple integrals. And in doing so, we need to compensate for the dA or dV. So much like in a U substitution, and here's our U substitution example, when we change the variables from X to U or something else, we need to compensate to change the dx into something. So the dx will include some sort of compensating function that is related to the differential. And in some cases, most cases, we also change the limits of integration so that we can integrate with respect to that. Sometimes we go back to the original variable x and then put in the x limits, but sometimes we can take a look at doing this, changing variables and changing the limits as well. And if you remember in polar coordinate transformation, when we have something that is like circle related in the xy plane, we have this polar coordinate compensation for the dA, where dx dy becomes dr d theta, and then we add on that extra r, and that extra r comes from the change of variable theorem that has something to do with this thing called a Jacobian. So first of all, let's establish some ideas with the changing of the variables in the first place. They call this a planar transformation. Planar transformation is a transformation, basically a function from R2. This is R2. Where's my pen? This is R2 to R2. Except in one R2, in the first R2 here, we look at this as if the variables were R and theta. And in this other R2, we look at the variables as if it was X and Y. Okay, but still, it's from 2 dimensions to 2 dimensions. And our transformation looks like this, where we say X is equal to R cosine theta and Y is equal to R sine theta. That means it transforms something that might look rectangular like this. This is, they call this D star maybe. And then this is D, the area that our integral is originally trying to integrate over. So in this transformation, it takes a rectangle into this, and we can look at backtracking and say, hey, this is the shape that we want, a semicircle, and when we backtrack that to R and theta, your limits become R going from 0 to 1 and theta going from 0 to pi, right? We never look at really the two-dimensional domain like this as a rectangle, because we're so used to looking at radial distance r and angle theta from just what's happening in the xy plane. But really, when we change the variables, our limits change to something that's more manageable, which is the whole reason why we would do the change of variable in the first place. Just as a few more pieces of information that is important mathematically, but not so important for us, because we're just going to kind of wave our hands to this. We say that a transformation is one-to-one if no 2 points get mapped to the same image. So that's just the definition that they had. I don't know why I have it there. It's not that important. But in any case, Here's an example of a transformation, and let's see if we can visualize and picture this. So let's say that our t goes from R2 to R2. That's our transformation. And in this R2, we have a U and a V, and that's our input. And our output in R2, in this R2, is going to be your X and Y. And then this transformation tells us that X is going to be U plus V and Y is going to be 3V. And find the image of a rectangular region in UV space that goes U from 0 to 1 and V goes from 0 to 2. And just to let you know, in most cases, for us, we're going to be considering these functions that are generally linear functions. So in this case, they want us to say from the UV plane after the transformation into the XY plane, and then show that t is 1 to 1. Let's skip over that. So what we want to do is we want to figure out what happens to the points, and let's actually look at these points. The key points in our rectangle are like the corners, right? So we have 0, 0, we have 1, 0, we have 1, 2, and we have 2, 0, or 0, 2. All right, so if we can find out what happens to those in the XY plane, then we can kind of figure out what happens to the figure. So let's say 0, 0. You put that in for U and V. So this is U and this is V. So X will equal to 0 plus 0. Y is going to equal 3 times 0. So that gives us 0, 0. So that maps this point 0, 0 to this point 0, 0. Okay, that seems kind of redundant, but that's good. Now let's take a look at 1, 0 and see where that goes. So X is going to be, remember that this is U and this is V, so this is 1 plus 0, and Y is equal to 3 times the second component, which is 0. So this is going to go to 1, 0. So far, we have this set of points here that looks like it goes to this set of points here. All right, I think the interesting part happens after that. So if we take a look at what happens to 1, 2, where 1 is U and 2 is V, X is equal to the sum, so that's 1 plus 2, and then Y is equal to 3 times the second component, 2. So our XY is going to be 3, 6. So now I go 1, 2, 3, 1, 2, 3, 4, 5, 6, somewhere over here. All right. And then I figure out what happens to 0, 2, and my X is going to be 0 plus 2, and my Y is going to be 3 times 2. So that's also 6. This time it's 2 and 6. So 1, 2, 6 would be over here. So I'm looking at a parallelogram, and that is saying that this area here gets mapped into this area here. And I'm calling it D star and D because that's eventually that's what we're going to end up calling it. Okay. Now, sometimes we might be interested in the inverse transformation, and you can only do that if it's 1 to 1. The disclosure here, the polar coordinate transformation is not one-to-one. So in general, we're going to be dealing with functions that are just one-to-one. So to find t inverse, what we want to do is we want to take a look at this set of equations and somehow solve for this so that we can find u and v. All right. So what I would do is I want to solve for u and v. I treat it like it was like a system of equations by maybe multiplying the first one by -3, and then adding it. Oh, I probably don't need to do this. Yeah. And if I add them, I would get -3x plus y equals -3u. What? That was a temporary quick brain drain there. I'm out of space. So u should equal to, I'm just going to be sloppy about this, -3x plus y divided by -3. And v would just be, if I solve for this equation here, v would be y over 3. So that would be my transformation going backwards if I needed to. So technically, polar coordinates has this information also. You can go backwards from polar coordinates, although we rarely do that. We think about this relationship over here, but we also say, we can also say that r is equal to plus or minus the square root of x squared plus y squared. And then, well, let me just write it as the equation that we know better. R squared is equal to x squared plus y squared, and then tan theta is equal to y over x. So you can solve for this by taking the square root of r, or you can solve for theta by taking the arctan. But by doing those, you kind of lose some information. So because this particular transformation, polar coordinate transformation, is not one-to-one, the solving back would be a little bit trickier. But again, we're not going to dwell on that too much. But here is your t inverse. Okay?
So that transformation, that's not like a standard transformation. That's just like a transformation that the problem gives you.
Yes. Yes. So our standard transformations are polar coordinates in 2 dimensions and then cylindrical and spherical coordinates in 3D. Anything else is really non-standard and depends on the problem that they give you. Good point. All right. So that is the introduction. This is like the u substitution that you would make. And then from the u substitution, you would take the derivative to figure out what your dv is and stuff like that. So for that, we need the Jacobian. Oh, they give us another problem. Should we do it? Let's do it. All right. So the way this problem is now in this example, the way this problem is stated, we consider this transformation u is equal to this and find the related inverse. So let's find a related inverse first. So just like what we did, we're going to want to write this in terms of x and y. So right now this is u is equal to something and v is equal to something. We're going to want to write it as x and y. So let's rewrite this. U is equal to y minus x and v is equal to y. Now I want to write this as x equals something and y equals something. And to do this, well, I have y is equal to v. This isn't always going to happen like this, but it sure is convenient. If y is equal to v, or v is equal to y, then y is equal to v. So that part's done. And to get x, I would probably take subtract. It doesn't matter what we subtract. Maybe I'll subtract the first one. Multiply the first equation by -1. That way I can make the x positive. You could do this any way you want. And then I'll rewrite v is equal to y, and then I will add that. So I have v minus u is equal to, the y's would cancel, and then I just have x. So my x is actually equal to v minus u. So that's the inverse transformation that they're talking about. Okay? And really, this is what we need to find a Jacobian. Now, for the next part, find the pre-image of the parallelogram with vertices that look like this. So the pre-image tells us that we're going to create a transformation where we have xy here and uv here, and our transformation goes this way. That means this is a transformation that we're actually looking at. X is equal to v minus u, and y is equal to v. Just like,
do you know from the problem which way you're going?
because they say find the pre-image, our transformation are generally going to go from t, and it's going to go from uv to xy.
The pre-image is UV.
The pre-image is uv.
Okay.
Yeah, so the image would be your output. The pre-image is your input. And so what they're saying here is that you have a parallelogram on the xy plane that has 0, 0, 1, 0, 2, 1, and 1, 1. Oh, they kind of wrote this backwards. Not backwards, but it didn't seem to be in order. But this is your parallelogram. And this is what they're calling R. And the pre-image goes back, and then this is what we're looking for. All right. Now, this set of equations tells us how to get from uv to xy. When we want the pre-image, what we want to do is we want to use these equations where we have y minus x is going to be equal to u and y is going to equal to v. And that's how we're going to get the pre-image. So we're going to put in points like we did last time. When we put 0, 0 in for u and v, or in for x and y. So I'm working backwards now from last time. This time, this is your x and y point, and the pre-image is going to be like the t inverse. If x was equal to 0, if y was equal to 0, this is 0 minus 0. And this is going to be equal to 0. And then for the second one, y is equal to 0. Oh, sorry. Let me write. X is equal to 0 minus 0. And y is going to be v, which is 0. So your point here is going to be 0, 0. And then let's pick 1, 0. And so the t inverse of that is going to be y, that's 0 minus 1. So 0 minus 1 That's negative 1. And my y is going to be v, which is the second component. So our point is going to be negative 1 comma 0. So negative 1 comma 0 is over here. And then we keep going. We'll put 2, 1 in. So the t inverse of that is going to be x is equal to y minus, so y is 1, and then minus x is 2, so that's negative 1. And y is going to be just v, which is a second component. So this will give us a point negative 1 comma 1. So negative 1 comma 1 is over here. And then our last point 1, 1 is going to be x is equal to y minus x. And then y is going to be the second component, which is 1. So that's 0 comma 1. And that is up here. So now instead of integrating over a parallelogram R, we're going to integrate over a new region that is a nicer region to integrate over, right? So if I were to integrate over this, I would say, hey, this is like u goes from 0, oops, that would be negative 1 to 0, and v would go from 0 to 1, which is nice constant limits. On the other hand, if you were integrating with R, I think this would be better integrated if we looked at this as a type 2 region. So a type 2 region says your x is going to be between a couple of lines, and then your y is going to be the constants from 0 to 1. And figuring out those lines would be not difficult, but more tedious than if you had constant limits, for sure. So I don't know if that's really the motivation for doing this change of variables, to have an easier set of limits to integrate over. All right, so the Jacobian is this differential that you would need to compensate for changing your variables. But what you need is you need your original x as a function of the two new variables. Just like we had x is equal to r cosine theta and x is equal to r sine theta. Here we have x is equal to some function of u and v, and y is equal to some function of u and v. And this is a little tedious looking. Let me see if I put parentheses, if that'll be any better. But it's going to be the derivative of x with respect to the first variable, and the derivative of x with respect to the second variable in the first row, and then the derivative of y with respect to the first and second variables, and then the determinant of that. So that determinant is going to give you your Jacobian. So that's your Jacobian, and the theorem tells us that if you want to change variables, and I tried to be consistent with their notation here, if you want to integrate over R, and that R seems to be a little complicated, whether it's a circle or like a parallelogram like this R, and then you want to change variables so you have a nicer set of limits with u and v, I think I was calling this R star, so let's call it R star. Oh, what happened? R star. Oops, that's an 8. R star. There we go. Then that means you have to change your x and y values inside of your function if you had an integrand, and then you have to multiply by the Jacobian. So this is like that u substitution where you multiply by the the derivative, some sort of derivative in there. So if you look at in polar coordinates, what you have is a double integral over the new domain, and then you have f of r cosine theta because x is equal to r cosine theta, f of r sine theta because y is equal to r sine theta, and then this thing happens to be r, which I kind of showed you already one time, and then dr d theta, where instead of u and v, we're specifically using r and theta. Okay? All right, so that's a little bit of the theory behind it. Let's take a look at the strategy and then do an example. So the strategy is that when you're integrating something, they ask you to figure out what your integral, what your domain that you're integrating over. And so what you want to do is sketch that on the xy plane. And then you want to write the equations of these, they call it curves, but in most of the problems that you'll run into in this section, they're all just going to be lines because that'll just be easier. If they start becoming curves, it starts getting a little crazy and a lot more difficult to find those transformations back and forth. Not impossible, like, for example, polar coordinates is an example that's not a linear transformation. Okay, depending on the region and integrand, choose to transform x and y into something with a u and v. So that's the t transformation that you're looking for. This is your t transformation that goes from uv, that's our input, and our output is xy. And then you've determined the new limits, because what you would do, or what you should do, is draw your new region. So draw region on the UV plane. And then find the Jacobian, and then put that Jacobian in for the dA. So the dA is going to be replaced by the Jacobian times the du dv limits that you have. All right. Now the idea is that we hope that they give us this thing, the actual transformation, because otherwise it gets a little bit difficult. All right. Like, for example, this problem here, they don't give us a transformation, but they give us, I found this problem as one of your homework problems, I think. So they gave you a hint in the homework, and so I didn't put the hint here, but we'll apply that hint here. So I actually drew this, except I don't have a link. So just to save some time, I'm going to go into my Desmos and see if I can find this. I think this is the most recent one I just did. All right. So I have negative 6x plus y equals 0. So that's a line going through 0. If you solve for y, I think that has a slope of positive 6 or something like that. So it's fairly steep. Here is the same thing, except I have an intercept at 8. Here I have 6x minus 5y is equal to 1. You can graph that as well. That's just going to be another line. And then you have another line over here. So I graphed those 4 lines ahead of time, and it looks something like this. And I'm guessing this is the part that we want to shade. Okay, so let me take a picture of that to put in our notes. This is, looks like most of it is happening, all of it is happening in the 3rd quadrant. Not that that makes it any easier. right, so these are your 4 lines. This makes up the parallelogram. And if you look at it carefully, you can see the enclosure part of what you're looking for. So we are looking at this thing over here. Now, if I want to try to treat this as a type 1 or type 2 region, it'll be a little bit difficult because right close over here, if I draw a vertical line, I would be saying that, okay, I can integrate from here to here, but then I have these extra spaces on the outside of that. So I think if I were to treat this as a type 1 region integral, I would need 3 separate integrals to figure this out. The next idea is to see if we can make this into, do a linear transformation or do a transformation so that I have this XY space that I'm going to change back into the UV space. I should have put this a little bit further over here. Let's see. Okay, let me erase this so that I can physically move this over here and say that this is my UV space. No, XY space. And then this thing here that was shaded earlier is my region R that I'm integrating over. All right, now the hint was to let U equal to negative 6x plus y, and then let V equal to 6x minus 5y. Now, why did they do that? If I did that literal replacement here and say this is equal to U and this is equal to U, I will have U is equal to 0 and U is equal to 8. And if I did that literal replacement for this thing as V, then I'll have V is equal to 1 and V is equal to 4. So that actually, without doing what I did before, because before what I would do is I would find these corners over here and try to map it back, right? That gets a little bit complicated. So now, with this information, I literally can just say on my U V plane that U is going to go from 0 to 8, and V is going to go from 1 to 4. And those corners that are in this parallelogram will get mapped to the corners here. And this is now my new R star, which is going to be my limits for U and V. So instead of having limits for X and Y over here, I'm going to have limits for U and V. So what does that mean? My transformation, T, takes us from this rectangle to this parallelogram. All right, I actually don't have T yet because what I wrote down over here is a way to get from XY to UV. So this is actually T inverse. That would be if I want to go backwards. If I want my Jacobian, which I'll need to replace dA, if I want my Jacobian, I need to solve for X and Y so that I have X is equal to something and Y is equal to something for my T transformation. So how do we do that? We did it like we did before. This has a negative 6x and a positive 6x, so already I think I can work with that. I can combine that. if I just add this, I have u plus v is equal to, this is going to go away, and I have a negative 4y, right? And then I would say y then will equal to 1/4, negative 1/4 u plus v. Okay, that's fine. And then now I need to replace this with one of these things to solve for x. Maybe I'll choose this one and say u is equal to 6x, negative 6x, plus y, negative 1/4 u plus v. So what is that? I need to solve for x. I'll add this whole term to the other side. So I have a u, and this positive becomes a negative, or this negative becomes a positive. I got a 1/4 u plus 1/4 v is equal to negative 6x. Right? And then maybe I'll just write negative 6x is equal to 5/4. 5/4 u plus 1/4 v, and I'll finish this off by solving for x. Divide by negative 1/6, 5/4 u plus 1/4 v. I might want to rewrite that just so it'll be a little bit neater. So that is that. So that now I can replace x here is equal to, again, I was going to rewrite this so it's negative 5 over 24. Negative 5 over 24 u minus 1 over 24 v. And separate it as possible because I'm going to want to take derivatives of this. Our y is equal to, that's up here, negative 1/4 u minus 1/4 v. Okay, so that is our transformation. So in this particular problem, in some problems they'll give you the transformation straight up, and in which case, okay, great, I have x is equal to something, y is equal to something, I can do my Jacobian real quick. But here, they didn't give us any transformation. They gave us a hint to say let u equal to this expression and let v equal to this expression. And then by doing that, we got a nice rectangular region on the UV plane as opposed to this weird parallelogram business. So now we have the transformation. Okay? All right, from here we, according to this, we sketched the problem in the xy plane. The equations form the boundary. Depending on region, integrand, choose a transformation. So we found the transformation t. We just found that. Determine the new limits on the UV plane. We got that because of the way we did the transformation. In fact, let's be explicit here and say, okay, u is going to go from 0 to 8. And v is going to go from 1 to 4. Okay? So now we got that. That was step 3. Find the Jacobian, step 4. So let's do the Jacobian. To get the Jacobian, we need, I'm going to not do the curly d, but instead do the subscript. So x, derivative x with respect to u, derivative x with respect to v, derivative of y with respect to u, derivative y with respect to v. And then you want the determinant of that. So I take a look at my x. I take the derivative with respect to u. That is negative 5 over 24. And then 0, because with respect to u, the negative 24v goes away. And then I'll take the derivative with respect to v. That's negative 1 over 24. And then now I'm in the y equation. Take the derivative of that with respect to u. That's a negative 1/4. And then take the derivative of y with respect to v. That's also a negative 1/4. And now the determinant is just, this thing. So what's 4 times 24? 16, 4, 96. Yeah? So this is negative, negative, so it's a positive 5 over 96 minus a negative, negative, so that's another positive 1 over 96. So 5 minus 1 is 4. I think that goes in, right? That's we got 24 in the first place, 1 over 24. So the Jacobian is 1 over 24. Generally, by the way, let me go back to the theorem. We want the Jacobian, that's not the theorem. If I go back to the theorem real quick, we want the absolute value of the Jacobian. So if you got a negative number, make it positive. All right, so this is our Jacobian. Now let's go back to the actual integral that we're integrating. Come on. Actual integral that we're integrating. Let me see if I can highlight it. So you're going to make the appropriate substitutions. Oh, I'm sorry. I remember this problem. I think I put the negative in the wrong spot, so I want to put it in the right spot now because I think I mistyped this when I was typing it. The negative is just for the -6 because I remember seeing this and say, oh, this is one of our substitutions. -6 plus y is equal to u. So remember that u is equal to -6 plus y, and v is equal to 6, or 6x plus y, and v is equal to 6x minus 5y. So that actually changes my integrand, where we're going to integrate over the new region, which is just a nice square or rectangle. And then our top numerator here just becomes a u, and our bottom, our denominator here, just becomes a v. And then our dA starts off with a Jacobian, and then du dv in whatever order is more appropriate. In this case, because they're constants, it doesn't matter which way we do it. So let's do the du dv since it's already written like that. So we have 1 over 24 is constant, so let's throw that outside, u over v, and our u limits go from 0 to 8. Our v limits go from 1 to 4. All right, so we can actually, because this is like saying u times 1 over v, we can split this up to 2 separate integrals. So the u integral, 0 to 8, is just going to be u du, which is going to be u squared over 2. Our second integral from 1 to 4 is going to be 1 over v dv, which is the ln function. So we have 1 over 24, 1/2 u squared from 0 to 8, and then we have ln of v from 1 to 4. So 1 over 24, 8 squared is 64, 64 over 2, and then this is ln of 4 minus ln of 1, ln of 1 is 0, 64 over 2 is 32, so this is 32 over 24, ln of 4. I suppose you can, what is this? Divided by 4, 8. 4 over 3, 4/3. Okay. That's how we do transformation. Any questions?
This is all on the test, right?
Yeah.
Yeah.
Yeah. It comes directly from your homework, so make sure you do your homework. At least the computational portion. The one that's my MATLAB, my open math portion. All right. Let me show you the three-dimensional counterpart. The three-dimensional counterpart would be a 3x3 matrix, and finding the determinant of 3x3 matrix isn't that easy, so I won't give you any questions like that on the test. In fact, I don't even think it's in your homework. Yeah. But I did want to show you the Jacobian, how to compute the Jacobian, or how the Jacobian is computed for spherical coordinates, because I think I mentioned it, and then I said, oh, it's going to be a long computation. So I'm not going to do it, but I actually typed it up already. So your transformation in spherical coordinates is x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. And so the Jacobian needs the determinants of each of these things with respect to rho, phi, and theta. And so you got this determinant with respect to rho, phi, and theta. And now computing the determinant of that looks like this. And this is in linear algebra, where the determinant you get to expand on a row or a column. For each of these, you get these weird expressions, but I said all you got to do is find ways to factor things out, because things do factor out. And so if you want to follow along, things get factored out, and you get a bunch of sine squared plus cosine squareds after you factor things out. And then in the end, you get your Jacobian, which is rho squared sine phi. Okay? Always going to be rho squared sine phi for spherical coordinates. And the theorem here tells us that essentially if you have a function and you're integrating it and you found some appropriate substitution, then you just do the replacement for your x, y, and z, and then you throw in the Jacobian. This, by the way, is the symbol for the Jacobian. I didn't dwell on that very much, but the Jacobian, the symbol for the Jacobian is the partial symbol with respect to the x, y, z variables, and then the partial symbol with respect to the new variables. Okay. Now, for this, I just want to do one quick example, and I'm hoping this is quick, like 5 minutes quick. And the transformation here will be based on making this look like a sphere. So right now it's not a sphere, it's an ellipsoid, because, well, if A, B, and C are all equal to each other, then it's a sphere. But assuming that A, B, and C are not all equal to each other, we need some sort of transformation. So I'm going to say U is going to equal to X over A. V is going to equal to Y over B. And W is going to equal to Z over C. Now, by making this substitution, the change of variable, and then you're replacing X over A with U, and you're replacing Y over B with V, and you're replacing Z over C with W. So if you do that replacement, your UVW is going to be a sphere, a perfect sphere. What does that mean? That means you're starting off an XY plane or XYZ space. with an ellipsoid. And what you want to do is you want to find something in the UVW space that is a lot nicer in your transformation. And so in the UVW space with this substitution, it looks like it's going to be the first variable squared, second variable squared, third variable squared is equal to 1. So this is just a sphere, which we have spherical coordinates to work with, right? Now we want to figure out our transformation, x, y, and z. We don't have that here. We have u, v, and w. So we need to solve for x. So x is equal to a times u, y is equal to b times v, and z is equal to c times w. So the Jacobian for this is going to be the derivative of x with respect to u, the derivative of x with respect to v, and the derivative of x with respect to w. And then in the second row, it's the derivative of y with respect to u, the derivative of y with respect to v, and then the derivative of y with respect to w. And then the derivative in the last row, the derivative of z with respect to u, the derivative of z with respect to v, and the derivative of z with respect to w. So this is a triangular matrix. The determinant of a triangular matrix is just going to be the diagonal multiplied together. So that's A times B times C. Now, if we call this E, the volume of E is what we're looking for. And if you remember, it's a triple integral of E with a 1 dV. But now with this transformation, with the change of variable, we go and look at this, and let's call this E star. And now the change of variable tells us that this should be equal to the triple integral of E star of 1, and then our dV will include the Jacobian. Which is the x, y, a, b, c times du, dv, d theta in whatever order we want. Or not d theta, du, dv, dw. Now this is a sphere, so we're kind of doing another change of variable. We're going to go to spherical coordinates. Instead of x, y, z, though, we're going to use u, v, and theta. So we're going to change this from u, v, and theta. We're going to go do another transformation, spherical. A spherical coordinate transformation where we have rho, phi, and theta. All right. So we're going to do this Jacobian here. This is the Jacobian ABC. Okay. We have the Jacobian ABC. And then now, as we change this into spherical coordinates, we have another Jacobian rho squared sine phi. And then the rho is just, this is a unit sphere, so it just goes from 0 to 1. And phi goes all the way down to pi. And then theta goes from 0 to 2 pi, because it's the whole sphere. We actually don't need to do this because we know that if the Jacobian is a constant, ABC, and du, dv, dw for E star, we know that the volume of a sphere is 4/3 pi r cubed. So it's just ABC times 4/3 pi, because r is 1 in this case. Okay? All right. If you got any of that, great. If not, don't worry about it. Not on the test. All right. Any questions? So that's a quick glimpse of, that's like a 5 or 10 minute explanation of a 3-dimensional Jacobian. Questions? Okay. What's going to be on the test? So computational problem has 17 problems in it. Oh, people are logging. Zoom seems to be working now. Sorry, I've already committed to not doing Zoom because of the issue. All right, computational portion will have 17 problems. So just as like homework, right? Chapter 4 and 5. So, and I was looking at it. It didn't have questions on the last 2 sections, so I added questions in there. But I also realized that there are no questions from Lagrange multipliers. What section is that? It's in, no, it's the end of chapter 4. It's the last section in chapter 4. Let me take a quick look at the book. Table of contents. Lagrange multipliers was 4.8. There is max-min problem, but it's classifying. So it's a second derivative test and not extreme value theorem. So I'll put.
And there are like limits too and stuff like that.
Good question. I don't remember.
Like the beginning of chapter 4.
Yeah. I don't remember. I didn't pay attention to that. Do you guys know about the no column? No and no. What? That's confusing. That's no and no. Everything, no. No extreme value problems. No Lagrange multipliers.
Oh, there's no Lagrange on
No Lagrange multipliers on the test. Oh, what's going on?
Is this true for the Conquer one as well?
I don't know yet. Let me focus on this first, because I don't quite remember. So computational. Sorry, I don't know what's happening here. Keeps blinking in and out. I don't want to touch this. Come on. Okay. It's the connection to my computer. All right. No. Everything else. The limits is a question mark. I don't want to look now, so I'm not sure. If you do, then it'll probably be 2 paths that have different results, and so the limit doesn't exist. All right, but 17 problems. I think there's one problem. The first problem is like 2 points. Everything else is worth 3 points in terms of the distribution. That makes 50 points, I think. All right, the proctored portion will have 22 questions. The first 3 will be the short answer questions that you all know and love.
The short answer question is going to be like, because last time it was kind of like memorizing equations, like knowing the equations and how they, is it going to be the same as that, or is it going to be more like
Don't remember. I'm gonna do this off to the side so I can actually take a peek and tell you in a little bit more detail. I just looked at it the other day and I can't remember what happened. All right. Some questions might include like the difference between type 1 and type 2 regions. How would you switch from Cartesian to polar or cylindrical or spherical and all that stuff. So those are some examples that might come up. All right, so those are the short answer questions. There'll be 3 of them, and then the rest will be multiple choice or multiple answers or true false. So you know, if it's a circle, then it's only one answer. If it's a box, then you could have like 2 or 3 different answers. So yeah, I think that's it. So that's my quick review of what's going to be on the test. You do have multiple chances, right? So there's 3 chances for the computational portion, and there's 2 chances for the proctored portion. All right, and I wanted to know who's going to be here, who plans to take the exam here in person. I think there was a handful of people that did it last time. So I just need to know how many copies. I'm just going to make like 6 copies, and hopefully that's enough. Everybody else will do it online, I'm assuming. Yeah. All right. Okay, any other questions? Anything else you could try to squeeze out of me? And I think that's all I can say about it.
Average values on there?
Maybe.
Nothing with like, is it like the probability average value?
Oh, no.
Okay.
No probability average values. No, for sure. Oh, I'm just looking now. I said no Lagrange for the computational portion, but there might be Lagrange multipliers here. So no and no column here. I remember here there are no, I can't remember now. Lagrange is here. And I think there are no, what's that, the physics problems, density, mass density. So there's a whole bunch of formulas there. If you want to write it in your notes, that's fine, but you don't need to write it in your notes. I'm not going to ask any questions about that. And I can't remember if there's a Jacobian question here. If there's a Jacobian question, it'll probably just be about the spherical, cylindrical, and the stuff that we've kind of dove deep into. But I don't want to say no Jacobian here because there's that part, which is technically Jacobian. So I'll just leave it like that. Okay.
Next class is Thursday?
No. I'm going to put this in the announcements. I don't think I did. I don't know if the announcements were posted yet. But, sorry.
Or next Thursday?
No, we are going to meet here.
Wednesday?
No, Tuesday.
Oh, Tuesday. Oh, right.
Even though the exam hasn't been due yet. So this is, thank you for that question. Here we are. So no classes tomorrow because of Flex Day. And if you're going to take the exam here in person in class, then you come on Monday. We will have class the rest of the week, Tuesday, Wednesday, Thursday, and starting new material. But the exam is technically due on this day, on Wednesday next week. So if you take the class in person, I'll try to grade it and give it to you by Tuesday so you still have an opportunity to take it, retake it online if you want. Okay? So we will meet on Tuesday next week. Yeah? Yeah. Yes. All right. That's it. Good luck on your test, and I'm going to try to process this so that this will be available for folks who didn't make it. See you guys. Good luck studying.